In this second video for chapter 6, I'd like to take you through an online simulation to illustrate a concept. And you're going to find that this is a little bit deeper of a concept. The web page that we're going to be accessing is going to be a page that you're going to be going into yourself and working on an activity. So it is worth your time paying close attention to what I'm about to be doing. Now we're going to take you over to this website right now where I have already identified a bunch of different data sets. Now I'm going to choose the data set called pennies, and I'm going to focus in on the ages of these pennies. Now, what happens when I choose this is they've got a rather large data set here already typed in with 1,000 pennies. And the age of all the pennies are listed here. It tells us what year the penny was and what age this was. Now, they actually created this data set back in 1999, and this has been sitting around for over 20 years. And this data set, basically, I think part of the reason they haven't changed it because of the subtraction across a century mark and people making mistakes with borrowing and carrying and all that. But notice how in this first row, there was a penny from 1995, and back in that year, in 1999, it was considered to be a 4-year-old penny. Okay, likewise, if we go all the way down to the 1,000th penny, which was 1999, it was a brand new penny at that point. It was 0 years old. So they've got 1,000 data values inside of this table. Now, at the bottom of this, they've actually got the distribution of all those pennies. And what I want you to notice are, well, a few things I want you to notice. First off, they've told us the mean and the standard deviation of those data sets. Okay, they've also told me there were 1,000 in the population. The second thing I want you to notice is the definitive shape here. This is definitely a right skewed curve. If we were to have done this in a physical classroom, we'd have a bunch of shiny pennies, which would be these first few bars, and there'd invariably be people bringing in some old moldy types of pennies that you have to scrape away that green stuff to kind of read off the date and all that. So bottom line is, that's kind of a realistic curve, but notice it is not normally distributed. That is the key point that we're making here. Now, can we use the normal CDF curve to calculate probabilities on a curve that's not normally distributed? Well, the answer is no, you can't. You need a normal curve to use normal CDF. And this is the population of all 1,000 pennies. But there's a little box I can check up here that's going to allow us to choose some samples. So I'm going to choose a sample of size. Let's go with size 5 here. And how many samples do I want to choose? I'm just going to choose one for right now. And if I choose draw sample, there's my 5 pennies. You can see on a single dot plot the most recent sample, which is just this one. And you see a little bar chart being started here. Big whoop. We've got the power of computers here. So let's change this to 100,000 data values. Let's hit draw samples, and we might have to wait just a second. And okay, here is the 100,000th sample. It illustrated. I don't really care about that middle picture, but look at what happened over on the right. I'm going to zoom in a little bit here on the right. Notice how we have 100,001 samples. Notice how we've got a mean and a standard deviation, but look at the shape. If I were to click on this overlay and normal distribution, looky there, that looks pretty much like a normal distribution. Are the ages of the pennies normally distributed? No. This is going to be the mean of a sample of size 5. I probably should have illustrated this a little bit better. When we are doing this, we take samples of size 5 We look at these 5, we add up the ages, divide by 5 to get a mean, and it's the means over here. The sample means is what's down here at the bottom right on our curve. The means will be normally distributed. Now that's pretty exciting because now we can use the normal CDF function on something that is normally distributed. We just have to make sure we're not dealing with the ages of the pennies themselves, but that we're dealing with the sample means. Now I'm going to take you back to our notes, and then we'll come back to this in just a second and make an observation. Here we go. It says for large enough sample size, we can assume that, ooh, what's this notation? Well, I'm going to write it down my own way. When you see this mu subscript x bar, I'm going to say the mean of the sample means matches the true mean. Okay? We can assume the mean of the sample means matches the true mean. Now let's go back to this online simulation that I had up a second ago. The true mean age of all 1,000 pennies is 12.264 years old. What was the mean of all of our sample means? Not 12.264, but it was pretty darn close, 12.244. So it was off by a couple hundredths of a year. Well, we only took a sample of size 100,000. I know that seems huge, but when you look at all the different ways I could have taken samples of size 5, that's actually a rather small sample. And we do have a little bit of sampling error, but if we had had a larger sample, then the mean of our sample means over here at the right should have been a perfect match for the mean of the actual data values on the left. So that's what I'm illustrating partly in this. Now going back here to our thing, it also says sigma subscript x bar equals sigma divided by root n. And this sigma subscript x bar is no longer called the standard deviation. When we divide by the square root of n, it has a new name called the sampling error of the mean. And we're saying if a random variable, like the age of our pennies of size n, is taken from a population with mu and sigma, then the random variable x bar is normally distributed. Okay, that picture we drew on the right side in our simulation was normally distributed with these two parameters taking hold. And it says for n sufficiently large, the random variable x bar is approximately normally distributed regardless of the distribution of the population. We'll illustrate that in a little bit. Now let's come back to this sigma subscript x bar equals sigma divided by root n. If I come back over to this problem right here, on the left, the true standard deviation was 9.608 years. The standard deviation of our means was 4.283. If we were to take this 9.608, divide it by the square root of our sample size 5, we should be pretty close to 4.283. So I'm going to actually do that on my calculator. Let's start with 9.608. Break out our calculator here. Clear the screen. 9.608. I want to divide this by the square root. Now the square root is above my x squared key. So second square root of 5. And when I hit enter, look at what we get there, 4.297-ish. If I go back over to our screen here, 4.297, then here we have 4.283. It's pretty close. You can see that it is kind of like we're describing, taking the population standard deviation, dividing by the square root of n to get this standard deviation value. You also have to realize that this 9.608 is already rounded, and the response that we have out here is rounded also, and that could be causing a little bit of error. So what am I saying here? I'm saying this population data set is skewed right. You cannot find the probability, for example, that or the percentage of pennies that are above 35 years old using a normal CDF. But I can do calculations using normal CDF when we're looking at the distribution of the sample means of a given size, provided we take a large enough sample. Now, let's go back to our notes here. And in this class, I'm telling you n greater than or equal to 30 is going to be considered to be a large sample. And I'd also like to show you a couple of diagrams that I've found on the internet. Okay, now let's take a look at this third column here, because this is a distribution that's definitively skewed right, just like the one we looked at. And it says, as we increase our sample size from 2 to 4, look at that 4, it's starting to look like a bell curve, right? Once we get up to 30, it is even more so a tall, skinny normal curve, but normal nonetheless. And I'm showing you in these first two columns that you don't have to start with a curve that's skewed to the right. You can have a uniform curve, you can have this triangular weird shaped curve, and as you start taking samples of size 2, then size 5, and you start looking at the sampling distribution of the means of those samples of the different varying sizes, then once you get down to sample size 30, it kind of looks like the curves are about the same, regardless of the population original shape. Now here's another graphic at the right that I found online, and I like this way because they've got this pink curve, and it says over here at the right, no matter what the shape of the population is, no matter if it's skewed left like you see here, then the distribution of sample distribution will be normal if n is large. And there you have what's going on there. Okay, so kind of an interesting picture there. And I like that this one also said that the mean is smaller than the median, because you notice the original data set was skewed to the left, which said the mean was going to be smaller. Okay, so bottom line is we now have opened the door to using the normal curve when the data itself is not normally distributed. We just need to be looking at the distribution of the sampling means. So I've got a couple of examples here to finish off this second video to show you how this is actually going to be used in action. I'm telling you in this first example, the length of the Western rattlesnake is normally distributed, and I give you the mean and the standard deviation. Part A is asking us to find the sampling distribution of the mean for samples of size 4. So this is just a definition problem. What is the sampling distribution of the mean? Basically, that's asking us find the mean and the standard deviation with this X bar subscript. Okay, so we use our two formulas. The mean of our sample means is equal to the population mean, and that should just remain 42 because that's what they gave us up above. And then this sampling error of the mean, this new value, is going to be sigma divided by root n. So 2.04 divided by the square root of 4. Square root of 4 is 2, so we're dividing by 2 here, and we get 1.02. That was just to introduce the vocabulary. Now in part B, it says, okay, suppose we take a sample of size 16 snakes. Okay, so it's almost like we're taking a trip out into the desert with our gunny sacks. And as a field trip, our job is going to be to go snag some adult Western rattlesnakes. Probably does not sound like a fun field trip that we want to participate in. But bottom line is we're going to catch some adults, we're going to stick them in this bag, and then we're going to go back to campus and we're going to measure them out. Okay, or we'll let the people in the science department do that, okay? Determine the probability that the mean length X bar of our snakes will be within 1 inch of the population mean of 42 inches. That is between 41 and 43. Okay, so what have I done here? So I've started by saying, okay, where did that 41 to 43 come from? If I go within one inch, I'm basically going 42 plus or minus 1, and that's what got me the 41 to 43. Okay, we want to know what's the probability that the mean length of our snake will be between 41 and 43. Notice when I wrote this using probability notation, I put X bar in the middle instead of just X. The last chapter, the binomial distribution chapter, we were just using X. Now we're using X bar. Okay, at this point, I'm going to do normal CDF between 41 and 43. There's my mu. But, and here's the big difference, I need to divide my sigma by the square root of n. When they are giving us a sample size, that is clue number 1, sample size given to you, and find the probability that the mean length is between these values. That's the clue that tells you, hey, we're going to be dividing by the square root of n here. So on our calculator, when we do this, out will come our answer of 0.9500. And I'll have you check that one on. You know what? Let me go do this one with you, just so we can all be on the same page together. So I'm going to clear this out. Let's go into our calculator, and here we go. Second normal distribution, going down to normal CDF, we're going to be going between 41 and 43 when the mean is 42. Our standard deviation will be 2.04 divided by, and I know obviously the square root of 16 is 4, and you could just type a 4 in here, but I want to make sure you know how to do this. So second square root, there's my 16 being entered in there. And when I hit paste and enter, there's the 0.950. Well, I probably should have ended that with a 1 by rounding there. So I'm glad I actually went and did this with you, because now I'm going to go change this answer to end in the value 1. Okay, let's do one more problem, and this should really hit home as to when you're going to do this type of procedure in a different way. And I like how part A and B are contrasted with each other. The average overseas trip costs $2,708 per visitor with a standard deviation of $405. Assume the costs are normally distributed. What is the probability that the cost for a randomly selected trip is more than 3,000? Okay, now this is a randomly selected trip. The data is normally distributed. So in this problem here, I'm just going to do what we were doing at the start of this chapter, from 3,000 to a positive infinity, when here's my mean and standard deviation. And you're going to get an answer of 0.2355. Now, the second problem says we select a random sample of 30 field trips and find the mean of the sample. We want to know, is the mean greater than 3,000? Now we're going to be doing the problem the same way, but our standard deviation of 405 will be divided by the square root of 30. You can see that I've got that right there on the screen. And so out comes our value here. And notice that this one is going into scientific notation. Remember that that E-5 means move that decimal 5 places to the left. So we really get 0.0000. 39254, which is a very small probability. Now, I do want to make one more final comment before I close this video out, and that is that I told you the data was normally distributed. That was necessary to do part A. It was not necessary for us to do part B, because in part B, when we have a large sample size and when we're looking for the distribution of the mean, the result of that central limit theorem activity that I did with you is then going to be that, hey, we can then assume we can use the normal CDF regardless of whether the distribution of the cost of these trips is normally distributed or not. It's an added bonus that it is, but it's not necessary that it be that way. Okay, so please pay attention in this chapter as to when you are dividing by the square root of n and when you are not dividing by the square root of n.